Okay. Okay. So first off, let's do one related to the stuff we did last time, which is that 4-3, 4-5 stuff. Let's look at this thing. Can you guys just do the first two derivatives of this formula? Okay, let's see. What's the first derivative? That negative is chain rule, right? Cool, I like that. And then second derivative, the negative 1/3 comes down and makes it positive, but then the chain rule is going to make it negative again. So it'll be 2 ninths negative 2 minus x to the what? Negative 4/3. I love it. Do you see how that's to a 4th power? So the second derivative, everybody see that? So this piece of this is always going to be, everywhere that it's not 0 or undefined, this piece is going to be, that piece is to a 4th power. It's going to be positive, right? 4th power makes things positive. So then the second derivative will always be negative. What does that mean? It's always, second derivative tells you what? Concavity. So if this is always negative, that means the function is always concave down. Do you have to know that at the moment? No, but we did it. I like to point that out. So when it happens, you don't freak out about it. All right? Okay. So let's see. Let's analyze this dude first. What are my critical numbers for the first derivative? Yeah, just 2. And why is it a critical number? It's where the first derivative is. No. It's where the first derivative is. It's a negative power, so when they go underneath, and if it makes it 0 and it's underneath, undefined. Good, I like it. Undefined. So if I analyze this sucker, 2, put a U up there for undefined. Like I've said before, when the derivative is undefined, that normally means it's some kind of infinite thing. And that doesn't mean the graph goes crazy. It just means it goes straight up for a second. Or straight down for a second, depending on which infinity it is. Does that make sense? For the slope to be infinite, it doesn't take a lot. It just has to, oh, I'm infinite. Oh, it sounds like it's going to be going way all over the place, but it doesn't have to. So now I can look at both sides of this thing. When I plug in like a 0, what do I get? I get 2 to the 1/3 is positive, right? I mean, when I'm analyzing this thing, I don't care about the number. I know, I look in your eyes, some of you guys are like, how the shit am I supposed to know what's in? It's positive, that's what's important. And then when I flip it, it's still freaking positive, times negative is negative. And then when I plug in like a 3, This will be negative. Cube root of that is still negative. Flipped is still negative. Times a negative makes it positive. This seems weird, and we're going to see how this can happen. You guys should actually realize how this can happen. We've seen this before. What could it look like at a max? The normal max would be like this. What could it look like at a min? Like that is the normal min. But how else could it look like at a max? Kinky, right? Or this kind of kinky. Right? We've seen those kind of cusp things. Right? In fact, what happens to the slope right there? It becomes undefined. It becomes infinite. So that's probably what this dude's going to look like. I like it. Let me try something. What's a cube root look like? Anybody know? Cube root function? Yeah, it's going to be like this. It's like a square root, but it's got the negative half too. Now, if I square this, basically make everything positive, this is going to flip. Doesn't that make it like this now? Doesn't it have that little cusp thing there? Okay, that's exactly what we have. We have a cube that's been squared. So it flips, and it's got the freaky little kink thing there. Because it's like, I can't go negative. Oh, shit. Do you have to know that going in? No. It's going to come out of your picture, right? So what is this the location of? Goes down to it, up from it. Min. At 2. 0. I love it. Now you guys do the second derivative. Investigate the concavity. You already know what the answer is supposed to be, but make it all official with the sign diagram, all that stuff. So again, it doesn't matter what you plug in. And if you just plug in all this in the calculator, that's fine, that'll work. But you really should be able to do this just by looking at it, because you don't care about the number, you just care about the sign of it. Anything to the fourth power is positive. Any real number to the fourth power is positive, as long as it's not 0, or we're not considering 2. That's where it's undefined, so screw it. So this term is always positive, times a negative. So it's negative everywhere except at 2, because that freaks out at 2. Okay, cool. So 2 is obviously a weird-ass spot for this thing, right? Or strange. Okay, so I know it's going to be concave down everywhere, basically. Is there an inflection point? Inflection point would be where the concavity changes, and the concavity doesn't change. It just has a place where it sort of rests or does something weird. Okay, I like it. All right, so to graph this thing, well, what can I get from the function itself? What's the y, the x-intercept? What's the x-intercept? 2, 0. What's the y-intercept? 0, 2 to the 2/3. Oh, shit, that is right. Okay. I got everything I need. So there's a 2. Everything's happening at 2, basically. 2 is a intercept, and it is a critical number. Is the location of a min the y-intercept 2 to the 2/3, is that right? Yeah. Oh, this shit, that is like 1 point something.
1.58.
Yeah, okay. So it's got a 1.58. Boop. This is not an inflection point, so it starts off concave down. Is everybody cool with this so far? There's really not a lot going on with this, but it is weird still. It's concave down, and then it hits, and then it's still concave down. So it looks pretty much like we expected it to. It's just been shifted over by 2. So just remember those cusps can happen. Don't feel like you've made a mistake just because, concavity. Normally we're used to if it's coming in and it hits, you're used to that being an inflection point and it's concave down, now it's concave up. I mean, that's your regular function does that kind of thing. This is not a regular function. Yeah, like it. Yes?
So if we're like graphing this with everything we said, we would know that it's a cusp because for the critical point of the first derivative, it's
Yes,
undefined
right there.
as opposed to
That's why
zero.
I label that with a U, so I can kind of look at it and go, okay, something really strange is happening slope-wise. 2 is in the domain of this function, so that's not explaining the weirdness. But now when I graph it, I'm going, oh, it's weird. Okay, I expected something weird. And of course, you can always just plug it in the old calculator, take a look at it, what it's going to look like anyway. But this explains why it looks that way. Okay. Oh yeah, okay. I want to take, I'm going to step back towards section 4.2. I'm going to take one step back to indeterminate stuff. So everybody got what they want from this here? You guys got to get over that quiz, man. Just let it go. Shake it off. Just make corrections to it. Let it go. Okay. What indeterminate forms did we talk about? What's the one that got everything started? 0 over 0. And then what's another one? The one that's related to this? I like it. And then there's one we talked about that didn't seem indeterminate at first. And then there's something like infinity to the 0. And then there's something like 1 to the infinity. So let's look at an example of one of those. Now think about it. You would think that something that's really big, if you raise it to any power, is going to be really big. But anything to the 0 power is 1. But does the power ever get to 0? No, right? This is a limit. Remember, indeterminate forms are the limit form of what I'm dealing with. They're not an answer. They're just a form that it tells me what to do next. Right? So anything to the 0 power is 1. Infinity to any power should be infinity. Those are like butting heads. Those are like immovable object, unstoppable force. Right? Spin. 1 to the infinity is very similar. 1 to any power should be 1, and something to the infinite power, you feel like it should. So this never gets to 1, and that never gets to infinity. They are kind of like competing with each other, these two ideas. Okay, so what about something like the limit as x goes to 0 of 1 over x minus 1 to the 1 over x. Ooh, that's yummy. All right, now watch. Do you remember how we did derivatives of things like this? Do you remember how we did the derivative of like x to the x? What did we have to do? We had to take we'll take natural logs of both sides and then do it implicitly and then solve again for the show, right? We're going to do something very similar. We're going to say we're trying to find the limit as x goes to 0 of this thing. Right? That should equal e to the limit as x goes to 0 of the ln of that thing. You let that sink in. It's like every day I like you less, Jeff. So what this tells me is I can see what the ln of that is, try to evaluate that limit, and then just raise e to what I get. That's what that says. Is everybody cool with that math right there? What is e to the ln y? 1, because the e and the ln cancel. So that is correct. So I can analyze this limit and then raise e to what I get. So what do I get to? So if y is this, and real quick, what form is this in? Let me make this a plus one so it's more technically right. What form is this in? As x goes to 0, this is going towards 1. So make that a plus in there, just to be on the safe side. And this is going to, as x goes to 0, this is going to infinity. So it's in the form 1 to the infinity. Now I want to be really clear. I don't want to see infinity in your work. I don't want to see infinity. Infinity can be an answer because it's a way to say it does not exist. These are just forms that things take on. They are not answers. They are not work. They just tell me that, oh, let me try to put it in the right form for L'Hopital's, right? So what's the ln of this? Okay, so I'm going to do this, and we know that at the end we have to raise anything we get to the e to that. That's what that's a little, bless you, the little thing I'm doing to let me do some work. Can you guys see how that's already a ratio? I mean, can I just write that as this ln over x? So then I'm looking at the limit as x goes to 0 of the ln of this over x. When x goes to 0, this is 1. What's the ln of 1? What's ln of 1? 0. And when x goes to 0, x goes to 0. All right, so I get 0 over 0. The classic form. L'Hopital steps in and says, I've got this. Right? I don't know why he sounds like he should be French. I don't know. So what can I do then? What's L'Hopital all about? Yep, they're in the top, so let's focus on, I'll do the bottom. There, I did half. It's always funny, Jeff. Yeah, so derivative ln of something is 1 over that thing, so it's just going to be the reciprocal of this, right? So it's x plus 1 times the derivative of x plus 1 to the, let me write it like this. All right, that's the rule, isn't it? That's the chain rule. Derivative ln of something is 1 over that thing. Bam, times the inside gets a turn. Bam. When the top is a constant, it ain't no quotient rule. That's bullshit. Right? That is really where you want to make it. Bring the bottom to a negative power. There's no need for quotient rule at all. So what do I get there when I do that derivative? Oops. What happens here with the derivative? The negative 1 comes down, times x plus 1 to the negative 2. No chain rule really, because it's just going to be a 1, right? And that's over 1. And I should be keep my limit in there. I really should, because you guys need to do that too. The limit is this is the limit as x goes to 0 this, is the limit as x goes to 0 this. Can I plug a 0 in and get something now? Let's try it. Plug a 0 and I get 1. Times negative 1 times 1 to the negative 2. which is negative 1. So is that the answer?
Wait, on the test, if you don't put the limit of everything, like that's a minus 1.
Something like that, yes.
Okay.
I mean, because if without that limits thing in there, you're not being honest,
Okay.
right? I sort of put a little arrow, but I really should say equals the limit of this, equals the limit.
This is 4.2, correct?
This is 4, where were they talking about? 4.4. L'Hopital rule section, which is 4.4. So if you feel like this is different, it's not. It's still L'Hopital's rule. Now, is this the answer? Well, how do I get the answer? I just evaluated this piece. So I got to raise e to what I got, right? So what is this limit? It's going to be e to the negative 1. So it's 1 over e. That always freaked me out. If I really, you guys have got to think about that. If that was going to 1 way faster than that was going to infinity, the answer should be 1. If that was going to infinity way faster than that was going to 1, the answer should be infinity. They are going to each of those things at about the same rate, so they sort of have a compromise value in between the two. That is in between 1 and infinity, right? Or in between 0 and infinity, to be honest. But this is still like a compromise value. Okay, maybe. Yes?
We don't have to use the ln of y if we don't have to.
So we evaluated this limit.
No, I know. So we have ln of y equals, right, yeah, that one right there.
And then we did the limit
Yeah.
of this, yeah. So we're doing the limit of, as x goes to 0, of the ln of y. We figured out what ln of y is, and I did it.
Got it.
Cool, I like it. It's very similar to what we had to do to take derivatives of something, function of x to a function of x. Very similar idea. Okay. Yes?
Are we finishing chapter 4 today?
No.
Majority of it, though.
Yes. All right. So that's that idea. That was that last freakiest indeterminate form. So yes, if this seems really weird to you, yes, it is. It's the freakiest form. Of course it is. Anytime we have to take the ln to do something and then undo the ln that we did just to look at it, that feels weird, right? But oh well, it's a method we could use. It works. Look, we did it. Now, I didn't skip 4.2 on purpose. I think I got really excited about 4.3 and 4.5. Just kind of forgot about 4.2. But this idea, this is really related to something we looked at before. It kind of feels like the intermediate value theorem, which is related to that monk in the mountain problem. Remember the monk in the mountain problem? Okay. So, to be completely honest, Rolle's theorem is a specific application of the mean value theorem. It's just that this dude, Rolle, he came up with this idea on its own. And then somebody else came up with this theorem, and they went, oh, that's just a specific instance. So we start with this, and then we generalize it to this guy. Let me set up the basic idea. If I have a nice continuous function, it's differentiable on A to B. It's continuous on A to B. Where f of A equals f of B. It's continuous, differentiable. Right? So it can't suddenly decide to just jump somewhere, and it can't do a little cuspy dude because that's not differentiable at that point. Everybody with me? How could I connect those 2 points together then? In how many different ways, really? It's really just kind of 2 ways, to be honest. I can either just, what's the easiest way to connect those 2 points? Straight across. And what would the slope of that line be that I just drew? 0. Any other way I connect it, so the minute I'm not going straight across, I'm like going up or down or something. So if I start up, what do I have to do to eventually connect back to this guy? I have to turn around and come back down, right? It's got to be continuous, differentiable. It can't have a cusp. It can't jump, transport it. Can't transport itself somewhere. So somewhere on this curve, there must be a place where the slope is 0. There must be some place where it is parallel to the straight across option. Now, on one level, I'm hoping to God you guys go, yeah. And it's because of all this, it's got to be continuous, it's got to be differentiable, right? This seems, hopefully this seems like that, but maybe some of you guys are like, I don't know what this shit's going on, but all it really says is if you start to go not straight across, you've got to turn back. Now, how many places could there be where it's flat, where it's got a horizontal tangent line? I could connect them this way instead. How many horizontal tangent line positions are there? I don't know, 1, 2, 3, 4, whatever. Right? There's one. There's one. There's one. But so the theorem says there will be at least one place on that function where the slope is 0. Does that by itself, does that make sense? Let that make sense. Some of you guys are scared. You're like, that makes sense. What the shit does this mean? Nothing's made sense yet. I like that. It's a little Pac-Man ghost. They got a lot of fringe. Now watch this. Let me just immediately follow that with the mean value theorem, because it's mean value theorem just says, what if I take this and turn it? The same kind of shit has to happen, except now it's not going to be 0. It's going to be whatever the shit that is. So if I have 2 points, all the same stuff, except f of a does not equal f of b. So I have a function. Here's a. Here's f of a. Here's b. Here's f of b. Now again, the easiest way to connect those 2 points would be straight line. What slope would that straight line have? What kind of scale is that? What slope would that have? Come on, you can be very specific here. What slope? What's the slope of that line? You could do it? Algebra? F of b minus f of a over b minus a. y2 minus y1 over x2 minus x1. Nothing amazing. I love you guys. You thought you wanted me to say 11 or something. No, of course not. How the shit can you say 11? You don't know any freaking numbers. But we're way past, I don't know any numbers. We're way past that shit, right? If I say, what's the slope? You don't go, I don't know any numbers. You tell me the freaking formula. So the slope equals f of b minus f of a all over b minus a. Now, the theorem, to make it equivalent, you guys see how that's, what am I going to do now? I'm going to draw a little line. What's another way I could have connected those two? I could have went like this, wee, or alternate, wee, it doesn't really matter, right? Or again, wee, right? But guess what has to happen? The minute I don't go straight, if I go away from it, I have to turn back towards it. And it's continuous and differentiable. I can't do any of that turnaround in a weird ass way. I can't go this way, transport. No, I can't do that. So somewhere here, there's got to be a point C where what is true? The same idea as this. The slope of the function is the same as the bird flies. Right, as the crow flies. So this right here, f prime of c would equal this. All the theorem says is it exists. If you have a function that is continuous on AB and differentiable on AB, and the two outputs there don't equal each other, there must be at least one point C where the slope at C is parallel, where the tangent line is parallel, the slope is equal to that straight line slope. If you start this way, you've got to eventually turn. You definitely have to eventually have somewhere that you're parallel. You'd hope to God I could draw parallel. It's almost like, how long did it take them to come up with that shit? I'm hoping some of you guys are like, well, yeah. Okay. Yes? Now let's do an actual problem with this, just to show you. You're like, what would the problem look like for this? Blah, 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 blah. Okay, so here we go. Let's try this one. This is perfect. See how Rolle's theorem is a specific case of this? Because if f of b equals f of a, then this is 0. So Rolle's theorem is encapsulated by this, but we give him credit because he came up with it before this was come up with. We're like, we'll give you some props, we'll give a name to your thing. Fantastic. Sometimes we could be nice. Sometimes math people can be. Let's try this one. Yeah. Gotta bring my stupid glasses. 2x squared minus 3x plus 1. Zero to 2. Really quickly, does that meet the requirements? What are the two requirements for this? So this is polynomial, right? So it's definitely continuous on any freaking interval, and it's differentiable on any freaking interval. Right? So will it be that way on those zeros? Yes. Is that cool? But you got to take a minute and just, say that. If you have 1 over x minus 1 and the interval is 0 to 2, no, it's not continuous at x equal to 1. 1 over x minus 1 does not meet the requirements, so it doesn't have to do what the theorem says. Nah. If you don't meet the requirements, the theorem goes, oh shit, anything can happen. If you do meet the requirements, then that kind of thing has to happen. There must be a C where the derivative is the same as the slope between those 2 points. So you guys, please calculate the slope of the line connecting those points on that function. F of 2, what'd you get for f of 2? 3. What's f of 0? 1. So you're just going to find the slope, right? So it's going to be y2 minus y1 over x2 minus x1. So your slope is what? Now you don't have to use C, but to be completely following the thing, there must exist. So what's the f prime of x? 4x minus 3. So there must be a C where this equals what? Where that function is parallel to the straight across option. Please let that just make so much sense. Please. And then as you get for C, you get C is 1. Thank God that C is in there. If you get C equals 7, you know you made a mistake. It's got to be in that interval. How we doing? Everybody decent with that? All right, see us. Now, I'm hoping you get to the point where we're like, well, yeah, duh, this only makes sense. But this is like a little building block for other theorems. You can just quickly say, well, the mean value theorem allows us to do this, because all this shit's been done already. It's already kind of set. It's like a little subroutine you call that. Okay. So let me get a little bit into what we're doing today, and then we'll take a break. Or do you guys want to take a break right now? It's either way. All right, let's get a little bit into what we're doing. Let's see. So we're done. We got up through 4.5. We're getting into 4.7. We don't do 4.6. You can look through 4.6 yourself if you want to. Okay. All right, one side of this is related to 4.7. The other side is all colorful, and it's 4.8. So when we look at the 4.7 side. I want you guys to work on this, get as far as you can. Just make you feel bad if you're not able to. This is 176 stuff here. Thanks, Jeff. The section we're getting into is calculus word problem kind of stuff. Optimization problems. We saw those kind of problems in pre-calc.